I am so happy to be here with you guys tonight. It's a very special night because we get to celebrate the beautiful new book by Lawrence Krauss, The Edge of Knowledge. Are you guys excited? What makes this a beautiful book? I think that one of the most important things we can learn to say to ourselves is, I don't know. And that's okay to say, instead of just making some shit up. How often do we hear people just make shit up when they could just say, I don't know, and wait a little longer for more evidence to show itself, and or maybe not. Sometimes I don't know is going to be a fine answer, and that should be enough sometimes. We can't know everything. The book is informational, and it's everything I want to see in a physics book because it deals with the most inspiring things, in my opinion, which is, what are we close to getting? What are we on the edge of grasping? And then that leads to, at least in my imagination, going to the unknown unknowns. And that's, as an artist, that's a very exciting place to go. And a lot of people wouldn't think this would be an artistic inspiration book, but for me, it is. If you're new to Pangburn, Pangburn is not a venereal disease. Usually gets a little laugh. Pangburn is now a community, a flourishing community that is grounded in good faith and helpfulness. And we have members in our community from all around the world that get together every day on our Discord server online to have conversations like the one Lawrence and I are going to have today. And it's free to join us. You just search on Google, Pangburn Discord, jump into the server. You're going to find the Pangburn Library, which is the ongoing text chats that we have going. And we have voice chats happening all the time. Jump into Trav's Tav one night, and you'll hear some interesting conversations. We have a digital tavern there. But we have a lot of fun, and we have people from all around the world joining us. And the only rules are, you got to engage in good faith, being sincere with your intentions is what I mean by good faith, and be helpful. And I think we all went to kindergarten, right? Everyone went to kindergarten? Okay, good. What we're going to do tonight is have about a 45-minute discussion, and then we are going to open it up to you guys for a Q&A. We're going to give you lots of Q&A time tonight. It's a very casual night. Don't worry if you don't have your question polished perfectly before you come up. This is a night where we can dare to be wrong on the microphone. You're going to get some back and forth time. My dream for these events is eventually we will all be on stage together, huddled and passing the mic around. Like that's my dream. And we're getting closer and closer and closer. A couple things. We have two big events happening in New York City. December 1st, Lawrence will be taking the stage to talk about the UFO UAP phenomena with Nick Pope, who's a guy you'll be quite familiar with if you've watched any UFO documentaries. There's always a guy with a British accent on there, kind of skinny guy with glasses, used to work for the UK government, investigating these things. That's the guy. So Lawrence and him are going to sit down. When I asked Lawrence to do this, he said, "Oh, man, I used to do those talks when I was way younger, man. I thought I was done with all that, but yeah, sure, I'll do it." And then when he looked into Nick a little more and he saw what Nick was all about, he realized Nick wasn't like the Stephen Greer or the Bob Lazar type. He's the guy that's really trying to get down to what's really going on up there. And then February 16th, is the next big God debate, which if you can't make it to New York City, we will be live streaming, and that will be between Dinesh D'Souza, every atheist's favorite guy, Dinesh D'Souza, right? But Dinesh is coming back, he's a trooper, and he's going to be on stage with Alex O'Connor, Cosmic Skeptic, and that's going to be an epic, epic event. And it will be available on our YouTube channel for everyone. So, let's see what Neil deGrasse Tyson had to say about Lawrence's new book. The edge of knowledge takes us on a stirring tour of the cosmic frontier, where our knowledge is incomplete, our understanding is fragmentary, and our insights are flawed. But that's precisely the terrain that science navigates daily when decoding the operations of nature. And for that, there's no better tour guide than Lawrence Krauss. He's a best-selling author. Please welcome to the stage Dr. Lawrence Krauss.
Some people here. Thank you. Yeah. Nice to see you. It's very nice. Thank you. Good. Some people showed up. That'll make it more, I like talking to Travis, but it's nice to have some other people here.
Well, it's raining out there. We're not used to the rain.
Yeah, I know. I was going to say, I saw it raining. I thought, oh, that's going to ruin it. But then I realized we were in Vancouver, so it probably...
Right. Well, how are you?
I'm fine. I'm in spite of the jet lag, which I don't normally get, but it's amazing. I live now on the extreme east coast of Canada, the part that never gets mentioned usually when people talk about Canada. And it's a 4-hour time difference, not a 3, and that extra hours, it's the same time distance as when I go to London, which I was a few weeks ago. But anyway, it's great, nice to be back in Vancouver. It's been a while, and it's nice to be back with you. It's been a while too.
Well, this is your 4th Pangburn event. You must like something.
Yeah. No, we've had some good times, and it's nice to be back, and I hope it'll be the beginning of other things. But it's nice to be back in Vancouver.
You also noticed my space pants / painter pants.
Yeah.
I've worn these for most Pangburn events, by the way. I've washed them a couple times in between, but...
Yeah, I know. Yeah, you're always like, the galaxy. Yeah, it's good. Yeah.
Well, I just wanted to check in on a couple things before we jump into the book. Believe in God yet?
I don't believe in anything. Belief is a word that scientists shouldn't use.
Oh, man.
Things are either likely or not likely. I mean, I use the word belief, like many things. I fall in the traps of common language, but belief is just a ridiculous word, right? Because it implies accepting things for which there's no evidence, and yeah, it's either likely or not likely. I do have a God detector in my backpack, which I could have brought out. It still says no on it, but anyway.
Yeah, I don't know. And I know you love triggering philosophers, because it's very triggering.
They're so easy to trigger. It's really...
When you say believe, because a philosopher would say that, belief is essentially how you feel towards a certain proposition, right? So if the proposition is God exists, you feel a certain way about that proposition. You either believe it or you don't, right?
Well, yeah, but that's got nothing to do with rationality. Although, as another philosopher once said, reason is the slave of passion, and that's probably true. I think we rationalize. In fact, I talked about it in this book, and when we talk about consciousness, that we invent stories to rationalize experiences that we might have to make it seem as if there's some rational reason for doing things. And so humans do that. But yeah, I mean, if you ask me what I feel, sure, I'm in that sense, although I used to say, like my late friend Christopher Hitchens used to say, he called himself an anti-theist. Yeah. And I used to say I was an anti-theist. His argument was, if there were, even if there were a God, he wouldn't want to live in a universe with one. And I feel that way too. So my feeling is to oppose the notion of a God, but that means I have to be skeptical of myself if I recognize that my predilection is to not want there to be a God. I should be ultra careful when I make the claim that there's no evidence for God, because I know that we all want to believe in Fox Mulder's language, and so I should be ultra careful to realize that that's my preference. But in spite of realizing that's my bias, I recognize the universe gives no evidence for. That's all. That's the whole point. There's just no evidence, and there's no need. We talk. You like to talk about it a lot, I know, and I get dragged into it. But there's this illusion that somehow the God question is important in science, and it isn't. It just never comes up.
I agree.
40, 50 years being a physicist, and I've never heard the word mentioned in any physics meeting.
Yeah. I think it's more LARPing. LARPing, people like go out, they imagine certain things are the case and they play as the character or as the person who believes in a God. I don't, when I see how people who claim to believe in a God, the way I see them act, it seems like they will play that way when people are looking or when they're thinking about it, but when they're not thinking about it, they're just kind of doing what everyone else is doing.
Yeah, I don't want to cast aspersions on an event. Yeah, I've been on stage twice with Dinesh D'Souza. I won't do it again. But
would you ever talk to Dinesh again? By the way,
I talked to him. Sure,
yeah.
I talked to lots of people. I learned from my friend Christopher Hitchens, who had the best, one of his good friends. He was a bulldog, but he was one of the most tolerant people I've ever known in terms of not canceling people because he disagreed with them. So I remember when I was at his place once, and we actually, before he died, he was going to have a filmed event, which would have been great, with one of his good friends, Antonin Scalia, okay, and me and him and someone else, and I would have liked to have that. But Dinesh is a pleasant fellow. He just spouts nonsense and does it for a living. And it's been very good for him. But we did debate on, what's it called, Intelligence Squared. And we won. It was easy to win. Yeah. I forget what the question was, but it was something about God. And him and a professor from MIT. But the reason we won, I shouldn't say this, but I will.
Do it.
The reason we won was that the non-believing part of the audience was trickier than the believing part, which maybe doesn't say good things about them. But so the way this thing works is that people vote beforehand on this show, and they, what their, is whatever their belief is, and then the program happens, and then at the end people vote afterwards, and then whoever changes most minds wins. Okay? But it was clear that the audience. So what happened, of course, is that the non-believers all said they believed. and there's, at least that's my opinion of what happened. Anyway, it was an overwhelming change. And I thought they were just trickier. And I would have done that if I'd been in the audience. So anyway.
Okay, well, one other thing I wanted to check in on before we get into the book is James Webb Telescope. Has anything come up for you that has turned a light on that made you go, wow?
Well, yeah, sure. Every picture, just like the Hubble Space Telescope. You can't see those pictures and not be amazed. And yeah, and in fact, unfortunately, there's this, I get emails all the time, people saying, hey, is it true the James Webb Space Telescope has disproved the Big Bang? And the answer is no. It's brought out questions, but again, at the edge of knowledge, at the edge of what we're measuring, the data is always, there are always inconsistencies in the data. That's what makes it the edge of knowledge. And so there was a ridiculous, in my opinion, New York Times article that I had to fend off a lot of email about, saying that basically there were all these things coming out that suggested the Big Bang, our standard picture wasn't true. And the point is that James Webb is designed to do a number of things, but one of the things it's designed to do is to look back to the first light, to the earliest stars, the first galaxies. Because in our picture, we're trying to understand how they evolved. And a really big question is we see large black holes, or what look like black holes, that are things called quasars. Black holes are really the most, if they're really black holes, they're really the most visible objects in the universe, because if they're galaxy-sized, as some of these supermassive black holes appear to be, then When things fall into them, they emit a lot of light. And the only explanation for these things called quasars, which are the most luminous objects in the universe pretty well, is that they're huge supermassive black holes and things are falling into them. They could just be things that look like black holes, and I've written an article with a colleague, and I see a professor here from Simon Fraser, who was at my university when I was chair at Case Western, who knows about this, but saying that maybe it just looks like a black hole and it walks like a black hole, but it might not quack like a black hole. And but anyway, so the question is chicken and egg argument. There are a lot of these things in the early universe. How the heck did they form? Did black holes form first and then galaxies coalesce around them? Or did small black holes form in galaxies and then combine and merge? And these are some of the questions that James Webb would answer. But one of the things that is surprising is there are more galaxies, apparently well-formed galaxies, because galaxies take a time to look like ours. Our Milky Way galaxy cannibalized lots of small galaxies, and still is. You know, the Large Magellanic Clouds and the Small Magellanic Clouds, and I'm still allowed to call them Magellanic Clouds. They're small satellite galaxies that will be cannibalized, and the Andromeda Galaxy, which is that beautiful galaxy that you see all the pictures of, that looks just like our own galaxy, and it is essentially just like our own galaxy, a nice spiral galaxy. It's heading towards us at about 100 kilometers per second. In about 5 billion years, it will collide with our galaxy. Not much. It sounds like a dramatic thing. You really won't know. The night sky, it'll get bigger and bigger in the night sky until it becomes part of our galaxy, and our galaxy will rearrange and become probably something like an elliptical galaxy, but there won't be much collision of stars or anything because most of it's empty space. But so that'll be a big merger. But so galaxies, to form their present structure, cannibalize small galaxies, etc. And I think people had expected to see these nascent galaxies in James Webb at early times that looked very different, and some of them do. But what seems surprising is there's more well-formed galaxies than imagined. And that's difficult to understand in terms of what's called the standard model of cosmology. But, you know, it's just, it doesn't kill any, it's just, it's interesting. And the trouble, of course, with our universe is we have a sample of one that we can measure. And most of the predictions of our models are statistical, because that's how we can work on, it turns out we think all of the structure in our universe comes from quantum mechanics, and things are statistical. And so you can make statistical estimates about what's likely to happen. But rare things happen all the time, and tails of distributions happen all the time. And there's another thing that, you know, is kind of claimed to be a big challenge, the Big Bang, the rate of expansion of the universe. Two different ways of measuring it come up with a sort of a 2 to 4% difference of the rate at which distant galaxies are moving away from us. And some people are making a big deal about that. And I'm a natural skeptic about everything, especially observations, new observations, because they're often wrong. And I'm old, which helps. And I'm old enough to remember when I was a young faculty member, there were two measurements of what are called the Hubble constant, this expansion rate of the universe. And one measurement was 100 kilometers per second per megaparsec. Doesn't matter what those things are, it's a number. With an uncertainty of plus or minus 5, 100 plus or minus 5. And there was the other set of measurements were 42, a lovely important number for cosmology. 42, I was rooting for that. But anyway, 42 plus or minus 5. Okay, now so it's obvious that the observers, their estimates of their errors were probably underestimates. Okay, now the difference is something like 69 versus 72. And by the way, at the time, when it was measured to be 100 or 50, more or less, I said, it's going to be 75, because it has to be somewhere between. And that's what it basically is. So, but though error bars in those things, 68 versus 70, the error bars are like plus or minus 1 now, apparently. And so people are making out a big deal about this potential difference. And maybe it's a big deal, but it's a difficult thing to do, and it's hard to estimate uncertainties in an experiment. you can estimate your uncertainties because you can twist the dials and you can see how things change. You can estimate the systematics. But when you're doing an observation and you can't twist the dials of the universe, then it's harder to know what you don't know. I mean, really, when you're estimating the systematic uncertainties of a scientific experiment, you're estimating the things in some sense that you don't know. The things that you think could bias your experiment. And of course, you can always miss those. And science is full of examples of missing those. Scientists try really hard to estimate them and really do a good job on the whole. But so I'm less, there are things that are interesting, and that makes life interesting. But I don't see anything that causes me to, to jump up and down. And in retrospect, it's going to be great. We'll have a whole night with my answer to one question. But
love it.
This will be self-serving, but that's okay. I am. There was a different time in the early 1990s when I got involved in looking at the data from cosmology and looking at all the data. It appeared to me and a colleague of mine at Chicago that it took me a while to convince him of that, but we eventually did, that the data was inconsistent with the picture of cosmology that we all knew to be true. And that time was that we live in a flat universe dominated by dark matter, and that was the standard model of cosmology. And the data was simply inconsistent with that. And so we wrote a paper arguing that the only solution to make it consistent would be something that's more ridiculous than the data, is to say that empty space had energy. And in fact, to make it consistent, empty space would have to have 70% of the energy of the universe. It was ludicrous. And we wrote that paper primarily because I felt it pointed out that some of the data must be wrong. Okay? And I remember talking to a few people. I remember talking to Saul Perlmutter, where I spent a month at Berkeley, at Lawrence Berkeley Labs, and he was looking at a way to measure the total energy of the universe in a sense by looking at supernovae, the rate at which the universe expands. And I remember him saying, we'll prove this wrong. That was in 1995, and 3 years later, they proved it right. And I was more shocked than anyone else. I thought the data had to be wrong, but it meant we had to have the biggest revolution in cosmology since I've been a cosmologist, that empty space had energy. And Saul and Brian Schmidt and Adam Rees won the Nobel Prize for that discovery.
Brian Keating, I had on my podcast pretty recently, and I don't know if you get this sense, because I know you've talked to him. Do you get the sense that he's trying to look at different models, trying to steer away from the Big Bang model?
Well, look, of course he is, because that's that's the other thing that scientists want to do, is they want to go in every day and prove their colleagues are wrong. Right?
It's a good thing.
And it's really important to realize that, because everyone thinks that everyone wants to keep the status quo, that scientists are invested in not allowing some fringe ideas to happen. Now, scientists are people. That's a well-guarded secret. But and so therefore, yeah, people do want their own pet idea to be right and other people to be wrong. But science progresses by proving your colleagues wrong, in a sense. And so, yeah, Brian, he's an observer, and I think obviously he would like to make a discovery that requires us to change our picture. But that doesn't happen very often. Most of the time, when you read something that's astounding, most of the time it's wrong. Remember that when you read the newspapers. Remember it if you read the scientific literature. When I read scientific papers, I have this rule, this mantra I learned from the publisher of the New York Times, which I used to write for. And he said, I like to keep an open mind, but not so open that my brains fall out. And so that's my mantra. If I read an article in a scientific journal, I say, in order for me to accept that, my brains have to fall out. I think it's likely wrong. Now, it doesn't have to be, but likely is the key word. What's likely? And speaking of the event that you've conned me into doing in New York, Richard Feynman talked about UFOs in terms of aliens, and he gave my favorite line, which I'll certainly use in New York. He said, I think UFOs, and by UFOs he meant aliens, okay, are much more likely due to the known irrationality of human beings rather than the unknown rationality of aliens. So you just, in the likeliness test, almost anything that you can imagine, no matter how absurd, is more likely than the claim that these are aliens. And it's true, anything you can think of is more likely from as a physicist, and I'll certainly try and argue that in New York City.
Mm-hmm. Well, to the book.
Well, that's a good idea.
I thought we could start at the beginning if you think there was one.
I think, there was something like a beginning. I mean, we can say with great certainty that the universe is, in its present form, is 13.8 or so billion years old, plus or minus, 0.1 billion years, so 13.7 to 13.9. The observers would probably say less error than that, but it's, it is. There's no doubt about that. The hard part is the first. Well, I was going to say the first second, but that's not the hard part. What people should realize is we can measure things and test our ideas back to at least the first second of the Big Bang. So we can test the major features of cosmology right back to, and now we can, with the Large Hadron Collider, we can test our ideas back to the first millionth of a second. But if you really want to think about this as a scientist, then the beginning is infinitely far away. Because the proper way of thinking about this is powers of 10. And in powers of 10, so you got 10 to the minus 1 seconds is a tenth of a second, 10 to the minus 2 seconds is a hundredth of a second, etc. And each power of 10 takes you back another factor of 10, closer to the Big Bang. And every power of 10 gets harder and harder to measure here in the laboratory. And to go all the way back to 0 is in some sense an infinite number of powers of 10.
And people can look this up if they look up the logarithmic scale.
Yeah,
right?
And but what happened at t equals 0 is we just don't know. We don't know. And as you said, I couldn't hear you that well in the back, but the first sentence of the book, I think, says the most important 3 words in science are "I don't know," and I think that's and we were talking backstage, and I don't know if you said, I think you may have said this, but that's so important now, especially this week and all. And I mean, in human affairs, to understand you don't know everything is so important, and that's one of the reasons why I write these things, because I think the lessons of science could be so much, can make the world a better place in so many ways if we use the techniques of science to assess our own situation. But anyway, we don't know.
Well, and I think that's why this book is more than a physics book. I really do. I think it's a book of how to think well. I do.
Thank you. Well, I mean, I think all science books should really be that. And that's really what we should be doing in schools, which is not giving students a bunch of facts, because facts are unimportant, because, my phone has more facts and more misfacts than I could ever have. Yeah. It's a matter of thinking about how to tell the wheat from the chaff, and how to ask questions, and how to think critically. That's what we should be teaching students in an era dominated by social media. So anyway, I think that's an important thing. But to get back to the beginning, we don't know, because we don't have a theory of quantum gravity, which is what we think is a theory that's required to. We have these 2 profound pillars of physics, at least 2, but 2 basic profound pillars. The quantum mechanics, which governs the way the world behaves on very small scales, and general relativity, which is a beautiful theory that describes certainly the way the universe behaves on large scales, and all scales larger than our scale. Gravity is largely irrelevant in this room. I mean, sure, you notice it when you try and get out of bed in the morning, but it's the weakest force in nature, and it doesn't impact on human activities at all in the sense of the processes that govern our lives. But on all larger scales, it does. But it is incompatible, we think, with quantum mechanics. And so a lot of people try and come up with ideas to unify that, and some people string theory or loop quantum gravity. There are a lot of people who make claims, but we don't have a theory that is clearly a theory of quantum gravity. And there's some people who claim we don't even need a theory, because maybe quantum mechanics, doesn't operate on very small scales. I would discount that. In fact, I think they're wrong, probably. But I would discount that there are some very smart people. My colleague of mine who won a Nobel Prize, Gerhard Tuft, who's one of the smartest physicists I've known and didn't, revolutionize the field in the 1970s. He's pretty convinced that quantum mechanics is an effective theory, that on smaller scales it's not true. But, I think he's likely wrong.
Yeah, if LHC would just, get to work and show us the graviton, we're good, right?
Well, LHC ain't going to show us the graviton, but it'd be nice if it showed us something new.
Yeah.
The Higgs was a big discovery, but it was a disappointment for me to discover that we were right. I always much prefer to be discovered to be wrong, because then there's new things to learn. That's what makes it exciting. I was certain the Higgs particle didn't exist, and I had a lot of papers ready when it wasn't going to exist.
When you say you were certain, do you mean certain in the incontrovertible sense?
No.
In the dogmatic sense?
No, obviously not. Because once I realized it was there, I changed my mind. That's the way it is. But.
And I think it's important to point that out, because there's a incontrovertible type certainty that people apply to things like, Christian dogmas and things like this that demand that you be absolutely certain, incontrovertibly certain about something.
Well, knowing the truth, knowing the answers before you even ask the questions, that's the real problem. And it's not just Christian dogma, it's any dogma. And as you've read anything I've written over the last 3 or 4 years, the secular dogma bothers me just as much as religious dogma. Anytime people make a claim that no one can question, the claim that there are more than 2 sexes, say example. And if you argue that sex is binary, then in some areas you're canceled. And the idea that you can't ask those questions and discuss this. In fact, I was just with another friend of mine, Charles, who's in the audience, a neurologist. He was shocked. I just wrote a piece for Quillette about the American Anthropological Association that canceled a panel that was going to talk about sex and gender in anthropology. And they canceled it for a variety of reasons, but one of which that discussing that would be hurtful to some people in the audience, in some anthropologists. And it would be, and even then they wrote another piece saying it would be transphobic to have such a discussion. This was about sex of skeletons, among other things, okay? And that's the antithesis of science. It literally is the antithesis. They don't understand what science is all about, which is science proceeds by dialectic. It proceeds by debate and discussion to try and achieve an understanding of where we're at. And to not even be able to have a discussion of sex and gender for fear it might offend people is what you would expect to see in a variety of places, but certainly one would hope not in a scientific society. And it terrifies me that that's happening more and more in this country and elsewhere.
Yeah, and that's where the minimum requirements for fruitful dialectic are not being met. So something's going on there where a dialectic that could bear fruit just can't happen.
Yeah, and usually we're seeing it in universities all throughout this country. This is not, maybe it wasn't the point of the event, but it bothers me that I can't not talk about it. Yeah, universities should be the one place where nothing is sacred. I don't think anything's sacred in general, but it's the one place where you should expect, and I said this a long time ago, the purpose of education is to make you uncomfortable. One of the purposes of education. If you're not uncomfortable, then you're not learning. You're not pushing yourself. And so, but we're living in an environment where too many students feel they should never be uncomfortable, and too many faculty and university presidents think that, it's better to not make them uncomfortable and be on the right side of that social justice movement, and then there's no learning.
So back to the first section on time, I have a major bone to pick with you about time machines, because ever since I was a little boy, I wanted a time machine. Didn't you all want a time machine?
Of course, we all do.
We all did. I even probably tried building one out of a cardboard box.
Before you go on, can I take a poll of the audience?
Yeah.
So there's 2 reasons you'd want a time machine. One is to correct the errors of your youth. How many people would like to correct the errors of the youth? Okay. And the other is to relive them. How many people? More people. I knew it. Okay. Just checking. Okay. Go on.
Yeah.
Sorry.
Well, And then, yeah, I think about it, and then I think maybe we're getting a little closer, and you read some things, you hear some things, you read Einstein, you look at a different thing, and then all of a sudden you come along in your chapter, and you say, we don't only need a time machine, we need a space travel machine.
Yeah, that's, I think that's the first time I wrote about that. I thought about it when I wrote my Star Trek book and a book after that called Beyond Star Trek. It's something that never is realized. It's sort of one of these trivial things that makes time travel even harder if it's not hard enough. I love H.G. Wells' book, The Time Machine. It's one, I love it. I love his stuff. But the problem is the Earth is going around the sun at 30 kilometers per second. Okay? So if you go back an hour in time, the Earth will have moved 3,600 times 30 kilometers, more than the size of the Earth. You would pop out in empty space, which would be a rude awakening. And so you have to have a machine that also moves you wherever the Earth is at the same time, and that's a challenge. But believe me, the time alone is a pretty big challenge.
We were talking that would make a really good sci-fi comedy.
Yeah,
right?
We had a different view of it. You wanted them to realize they wanted to do that, and I thought it'd be great to have a sci-fi comedy where the whole, all of society gets together and they make a time machine, and the guy pops out in empty space. It would have been, anyway, it would be
the end.
Yeah, the end. It would be everyone gets run over by a truck. But time travel. If you ask me, I spend a lot of time in the book and elsewhere showing that we can't show that time travel is impossible. In fact, general relativity treats space and time the same. And I can come to Vancouver and return home in space, so why can't I go to the future or past and return home? And the answer in general relativity is you can. You just have to find the right universe to do it in. Right. And the question is, do we live in a universe that allows time travel? And I think it's highly unlikely. My late friend, Stephen Hawking, who wrote the foreword for that Star Trek book, used to say that time travel was impossible. He actually had a party once where he invited time travelers, and no one showed up. and then he said, that was his argument. If time travel were possible, we'd already be inundated by tourists in the future. But I as you may have heard me say this before, I countered him that they all went back to the 1960s and no one noticed. So,
or they might not tell us, right?
Well, in fact, that's a new thing. That's not just true about that. That's true about aliens also. I think it's quite likely that if we ever get to discuss aliens, who I think, by the way, I think there is likely intelligent life elsewhere in the universe, although I think it's highly unlikely we'll know about it. But it's also the question is if there was a highly intelligent society, what interest they'd have in ever letting us know of their existence or even talking to us. So,
I mean, if I was an alien, I'd looked around and saw some people treat each other around here. I'd be like,
it's not just that. It's if they were really sophisticated, they'd have nothing to learn or nothing. In fact, they probably would sit. A friend of mine, I think Frank Wilczek and I have discussed this, that they'd probably just sit staring at their navels and going, because they knew everything anyway. There's nothing else to do. Anyway.
There's a piece here I wanted to read from page 35 on time. We don't know if the presently observed energy of nothingness, of space itself, is really a fundamental property or just a transitory one, like the energy that drove a presumed inflationary phase in the early history of our universe. So there's a I don't know there.
Yeah, I mean, we know that our universe, we think, I shouldn't use the word no. We think all of the best possible idea for how our universe came to look like it does today, and the only one we have, in my opinion, that self-consistently does do that is this idea of inflation. That at early stages there was a really rapid expansion in the universe, and it's a natural consequence of most of the extensions of our theories of particle physics. It happens in almost all of them. The hard part is getting it to stop, but there's a rapid expansion, and but in our universe it stopped. If it happened, it stopped and actually produced all the structures we now see. The great thing about inflation is it takes small quantum fluctuations, and if the universe expands very big, those quantum fluctuations turn into real classical fluctuations, and they become ultimately galaxies and stars and planets and people. So if you want to see quantum mechanics of the universe, just look around. And it's a beautiful idea, but that had to stop. If it continued to expand forever very fast, no structures would ever form. And so that stopped, and we have an understanding of how that can be, that it was energy stored in empty space because there was what's called a phase transition, the same as the kind of transition that when ice turns to water, water turns to ice. And when that happens, energy is released. And when you have a phase transition on a cold winter day, colder than normal in Vancouver, but freezing enough so that at just around rush hour, it's raining like now, but let's say it's much colder, then the roads don't freeze because the cars are sloshing around the water and all that. But then after rush hour, they suddenly freeze. You get black ice because it's the preferred state to be in. It's below zero, but the configuration's been in as water when it really wants to be ice. And in the process of freezing, it releases energy, okay? Because it's in the state it didn't want to be in. The lowest energy state at that time, at that temperature and pressure, is ice, and it was water. And so our universe could be in that kind of state where for a while it hangs around not being in the lowest energy state, storing energy. That would cause this big expansion, and then releasing it. Well, we are as I said earlier, we've discovered, and by the way, the number we estimated, 70%, is exactly what the observers discovered to be. 70% of the energy of our universe resides in empty space. But we don't know why. It's the biggest mystery in science, because we don't know if it's fundamental or if we're just in another kind of inflationary phase where something's going to happen. And the problem with that is...
And if you had to place a bet, because I do want to know if you had to place a bet, is it fundamental or emergent? That's the...
Well, it depends on the day. Really, it does. I mean, it's a completely uninformed bet. I think it's... It's crazy no matter what it is. I think it wouldn't surprise me if it was the absolute lowest energy of empty space, because that would... I like that idea, because that idea is completely inexplicable. Why empty space should have that small an energy confronts everything we understand in science right now. So I kind of would like that to be the case, because it would mean there's something really fundamental we don't understand. And the other reason I'd like it to be the case is if it isn't, and there is going to be another phase transition in the fundamental properties of matter, then when that happens, it could be that everything disappears, right? Because all the stable structures no longer become stable if we go to a different ground state. And the good news is you wouldn't know it. It happened at the speed of light, so it get you before you knew it was going to hit you. So, but I will say, I'm very happy that I wrote, I don't know, a dozen years ago, I don't remember how long, a paper, Saving the Universe, showing how you could have a phase transition. You could explain naturally why the energy of empty space was what it was. And if we were in an unstable state that was going to have a phase transition, but the way I worked out, that phase transition would not produce anything that would change our lives. So it's almost certainly wrong, that paper, but it might be right. If it is, I'll have saved the universe, which is good for a day's work.
I actually quite hate time. We've already burned 50 minutes.
Really? Well, I think I burned 40 of them in my answer to your first question.
No, it's good. This is really important. I was telling you this when we were having a conversation earlier about how surprised I was that you put a section on consciousness in this book, because literally every time I would ask Lawrence about consciousness, whether we were doing a podcast together or whether we were on tour, he'd say, I don't want to fucking talk about that. Like he didn't have anything to do with consciousness.
Yeah, it certainly didn't. I mean, because it's such a murky topic, and it's also such a difficult concept. And as I told you, and partly because I have friends, are good friends of mine in Phoenix, who one of them, she reads everything. And every week she would tell me about a new book on consciousness that unveiled the meaning of consciousness. And then I reminded her, which I think I mentioned in the book, that someone told me, or I read once, that, and I think it's true, that you can tell how much is known about a subject by how many books are written about it. Yeah. The more books, the less is known.
Yeah.
And you know, you only need one book on quantum mechanics, Dirac's book on quantum mechanics. That's all you need. Yeah. And that doesn't mean there aren't more of them. But on the other hand, this is addressing the key unknown, known unknowns. And by the way, the book in Britain is called The Known Unknowns. In Canada and the US, it's called The Edge of Knowledge, because The Known Unknowns is a quote from Donald Rumsfeld, who some of you may have heard of. And my US publishers felt that that would be too divisive if we had a quote from Donald Rumsfeld. So they changed it. It's a great quote. It's a, you know, I don't like the guy. I don't like the guy at all, but it's a great quote.
Wouldn't that have been good marketing, though? Like
I think so, but
they thought people were going to see the title and I can't. You know.
Yeah, I don't. With newspaper articles and books, the publishers have the final say, and The Edge of Knowledge is a nice title. It is. I forget where I was leading to, why I was leading that, but what your question was. But in any case, The Known Unknowns is for me, you know, that's why I talk about consciousness. Because look, if you're going to ask about fundamental questions, there's 5 sections. There's time, space, matter, life, and consciousness. If you ask what are the key frontier known unknowns about science, you have to talk about consciousness. And the other thing that I only realized after the fact, if I'd thought about it, would have been obvious to me, that makes this so neat for me. It was also fun to learn about consciousness and learn about some experiments about consciousness. So one of the reasons I write books is to learn things. Otherwise, it's always the same book over and over again. But and I know some people who do that. But anyway, something about consciousness. When I forget what I was going to say, I made that joke and I lost it.
That's right.
Okay.
Hard problem. Did you discover anything when you were looking at the consciousness issue of any value, or do you think it's just this deep hole of despair that we're still kicking rocks in?
It's a very, you know, now I remember what I was going to say before I get there. I was just going to say that what is interesting is that it's not surprising, perhaps, is that the deepest questions facing science are precisely the same questions that everyone asks who aren't scientists. Right. You know, how did the universe begin? Can you travel in time? Are we alone in the universe? When I see green, do you see green? It's the same thing. You know, all of the questions we ask are the same questions that science is asking. And I think that's interesting. And with consciousness, there's a lot been learned about the brain and the way it works. But when it comes to consciousness, I don't think we're much beyond the same questions that everyone asks about what some people say, and both philosophers in particular, but some neuroscientists would say, and it's reasonable, that consciousness is an illusion. Of course it is. We put together this notion that there's an us inside our brains, and it is an illusion, that there's some central control panel person there operating things. But saying that, you know, like many things philosophers say, means nothing, because the question is not, you know, okay, it's an illusion. The question is, how does that illusion arise? Everything we see is an illusion. The solidity of this chair is an illusion, okay? But this physics explains how that illusion arises. And so what did surprise me, and I read a lot of, I've known a lot of conscious people who work on consciousness and learned a lot from them, but I read books that I wouldn't have read otherwise. And what was interesting to me was that even the chapter before, I talk about what is life, and defining what life is a little surprising. The definitions you come up with for life, most of them are satisfied by fire, and fire isn't alive. But as hard as it is to define life, defining consciousness is harder. And most researchers who work on consciousness don't even try and define it, because we don't have an estrogen. Well, and after the book came out, I did an event with Noam Chomsky. Yeah. And he argued that maybe that's where you're leading, but he argued that, you know, maybe the whole question is just the wrong question. Yes. He thinks ultimately, in the best world, we'll have a mathematical theory of how things work, and we won't worry about the mechanisms in that sense. The example being just like electromagnetism the most foundational theory of modern science, James Clerk Maxwell's theory of electromagnetism, the 4 Maxwell's equations that physics students wear on their chest and t-shirts. When he developed that, it was, and to define it, he had a theory about, how the empty space worked with wheels and pulleys and all of that in order to get the equations, but we've thrown that out. Just have the equations. We don't think of the wheels and pulleys. And Noam has argued that we won't even talk about consciousness. We'll just have a mathematical theory of I don't know.
At this point, I think I agree with Noam on that. I had him on my podcast recently, and we talked about the same thing.
Yeah. Well, he's dogmatic about a number of things, but or I wouldn't. Well, anyway, he's sharp cookie. So, but anyway, it is what was fascinating. One of the things I really enjoyed doing there. I actually know this guy, Michael Gazzaniga. He's at UCSB. I think he's still alive. I lectured there with him. He's a neuroscientist. But he and also Joseph Ledoux, who's another neuroscientist I know at NYU. They were involved but Gazzaniga in particular, these split brain experiments where people who have epileptic seizures, they found that if they cut the corpus callosum, the thing that connects the 2 hemispheres, that it reduced the severity of epileptic. But it made them great test subjects because those 2 parts of the brain couldn't communicate together. And there's a great experiment that shows how people fool themselves. And the corpus callosum, by the way, is the thing that, because it connects the brain, sort of involves multitasking. That's why my wife says men have smaller corpus callosums than women, because so they can't multitask as well.
Lawrence does provide so many amazing examples like that in the book. He goes through Einstein and trains as well, and some really cool things in Maxwell. Now, please step up to the microphones. For anyone who has any questions, be brave. Even if the questions seem simplistic, I'm sure they are not. Thank you. Let's go.
Or now's your time to leave, politely.
Yeah, go ahead. You're first.
I'm going to apologize right off the bat for being late.
No worries.
But I've waited a long time to actually ask you this.
Oh, okay.
Is there anyone in the audience who's ever seen the Isaac Asimov debate about nothing?
Oh, yeah. I mean, Neil moderated
You'll have to
that.
help me a little bit with the first name. He was the expert on zero.
Yeah. Well, I got the philosophers mad at me because I said they're experts in nothing. Yeah.
Can you step a little bit closer to the mic?
Sorry.
Awesome, thank you.
Jim Holt was the next one.
Yeah.
The not philosopher. He's the...
he's a writer. He's a good writer.
Yeah, he was very clear about that. And he experienced nothing twice. Professional bowling and... and every night during dreamless sleep.
Okay.
Which you didn't love. Anyways. And then we had Mr. Bugle, Richard Goddard. Rich Goddard.
Okay. I can't remember who all was there that day.
Okay. And so he had a bugle and he had an idea of what nothing was. Yours was no time, no space, no energy. Correct?
Nothing is a very science is my whole point with that book and the discussion, which again, it's hard for classical philosophers to understand, is that our notion of what nothing is has changed dramatically. But that's okay. People think it's a cop-out. In physics, the difference between nothing and something is now largely non-existent, because nothing can become something, and something can become nothing. And so, and that's not a cop-out, it's just called learning.
Well, I think what the critique here is that a boiling pot of virtual particles popping in and out of existence is not nothing.
Yeah,
it's a state of potential.
That's the critique of people who haven't read my book, because
you address this.
Yeah, I know I address it, but there's all these, especially the religious ones. This may not be your question, but it doesn't matter. I'm answering it. Just wait.
I was actually going to give you an opinion eventually.
Yeah, but the point is, I'm not talking about virtual particles popping in. That's one kind of nothing. There are many kinds of nothing. That's the simplest kind. Empty space is one kind of nothing. That's the nothing of the Bible, by the way.
No.
But I'm saying that no, there was no space, no time, and that popped into existence. So there was no space. Everything we now experience did not exist in the sense there was no space and no time. But that's allowed if quantum gravity is correct. space and time can pop into existence. So it's not virtual particles in empty space. It's space and times themselves. Our universe didn't exist, and then it existed. Now, that may not be nothing for you, and I don't really give a damn, but that's, I think, a pretty good argument, but definition of nothing.
Sure.
Okay.
We won't talk about Eva and her string theory on the
Okay,
other
so what's
end.
your question that I haven't answered yet?
My question is, if you were to take yourself out, and this is not fair to ask, but I'm going to, if you were to take yourself out of that panel and looked at the other people's versions of nothing, which one do you think you would gravitate towards most?
No one's.
Oh, okay.
No, I mean, look, I think that...
Because Rich had an idea that outside of the emerging universes, the outside of the event
but
horizon,
the key point is there doesn't have to be an outside. It's easy, if you think it could be, although I think it's unlikely, but it could be that our universe is all there is. And space itself did not exist and then existed. And there's no, and so people tend to think of a closed universe must have something outside of it, because the Earth is a sphere and there's something outside of a sphere. But if you're on the surface of the Earth, if you're an ant, that's everything, okay? And you can have a closed three-dimensional universe, and there's nothing outside of it. There doesn't have to be anything outside of it. There may be, especially if there's a multiverse, which I think is most likely. I think it's quite likely that there are many universes now, based on what we know. And I even have proposed ways to indirectly try and just demonstrate that's the case. So it's not, if that's the case, it'll turn it from metaphysics to physics, which is always a good thing. But there doesn't have to be an outside, and I think it's a kind of misconception to think about what something would look like from the outside when there isn't necessarily an outside. So that's my problem.
Thank you.
Sure. That's a good question. Thanks.
Oh, hi. First of all, thank you for telling me that the book has a different title in England. I'm going there in January, and I'd hate to pay twice for the same book.
That's another good thing about having two titles, actually.
You won't remember me, but you and I indulged in some meaningful conversations several times at the Imagine No Religion conferences.
Okay. I do remember those wonderful
up in
meetings.
Kamloops a few years back.
Yeah, I remember. Run by a lovely guy. Yeah.
My question, you said during this evening, I can't remember the exact word you said, but you think that there is other life in the universe.
Oh, I bet they wouldn't be surprised to find other life in our solar system.
You think there's life elsewhere in the universe?
Oh, yeah, I'd be very surprised if there wasn't.
So my question is this, by your definition of the word, would that be a belief?
No, I said it's likely. It's highly likely.
Life in the clouds and Venus?
And it's based on evidence, okay? So I try and explain it in the book. Yeah. But here's the basic argument. It's pretty simple. So the first thing you realize that life evolved on Earth about as soon as the laws of physics allowed it to. Within 500 million years of the formation of the Earth, there were the oldest fossils formed. And now it couldn't have formed much earlier because there was what's called this period of early bombardment. As Jupiter was forming in the first 100 million years of the solar system, there were an incredible amount of stuff in the solar system, and it was bombarding the Earth, and it would have evaporated the oceans and everything. And we're fortunate. One of the reasons there's life on Earth is that Jupiter exists, because Jupiter acted like a cosmic vacuum cleaner that kind of swept out or knocked things out into the outer solar system. Okay, and when that bombardment subsided, it took almost 100 years for that, million years for that to happen. Within a very short time, life evolved. And so we know that there are certain ingredients that appear to be precursors for life on Earth. One is water, the other is sunlight, and the other is organic molecules. But all of those exist in profusion, not just in our solar system, but in the galaxy. One of the, you just heard about the comet bits that were brought back to Earth from, and they've discovered organics in there. But we can look at the spectrum of comets, and we can see organic materials. We can see the basis effect. We can see amino acids. Okay, so all of those exist in profusion, and so it's hard for me to imagine with there being 100 billion stars in our galaxy and 100 Now we know that almost all those stars have solar systems around them, so maybe 100 billion solar systems, that if they have the same ingredients, that hasn't happened. Now, but we don't know about that. I have, and the other thing is discovering life on Mars, extant, more likely extinct life on Mars, would not be evidence of two separate geneses. Because the other thing we've learned is that no planet is an island. Because we learned that materials, and if you're old enough, but some of the audience doesn't remember, Bill Clinton in 1996, I think, had a press conference in the White House where he basically announced the discovery of life on Mars. A Martian meteorite had been discovered in Antarctica, okay? A Martian meteor discovered not on Mars, but in Antarctica, which is why we go to look at meteors. I'm going to wake people up. Why do we go to Antarctica to look for meteors? It's white, exactly. So you take a snowmobile. I was volunteered, actually. I didn't get selected, but I wanted to go on and do it because it requires no skill. You just take a snowmobile and you drive around. If you see a rock on the surface of the ice, you know it came from up there, okay? And this meteorite from the Allen Hills in Antarctica had been discovered, and we know from previous missions to Mars what the composition of Martian soil is, etc. And this one, we knew it was from Mars. And when it was sectioned, these chemists in Stanford saw these small spherical globules that looked very similar to the earliest fossilized life on Earth, and measured from Australia and other places where the oldest rocks are, and some of them from Canada. And so it turned out they were 50 times smaller, though, but when it's grown up, and it was a big claimed discovery. Of course, it turned out that there are non-biological ways for that to happen, and most people now think that that was the case. But what it did force us to realize is that microbes, we all know about extremophiles, microbes could easily survive in a rock the voyage from Mars to, if they're knocked out of Mars by a collision, a comet or asteroid hitting Mars, and they could make the Earth, and they could potentially survive in a relatively inert state. So, as a friend of mine from whom I've learned a lot from, Andy Noel, who's a fantastic geologist and biologist, and on some of the Mars rovers teams, that if we discovered life on Mars, it would surprise him most if it wasn't our cousins, okay? But, so that wouldn't be definitive proof that there's been two geneses of life. But the great thing is we now know there are oceans in Europa, Enceladus, moons of Jupiter and Saturn, and they're separated by 5 to 10 kilometer thick ice, okay? And so they're separated. But those are spewing out organic water containing organic materials, okay? Yeah. And so there will be missions, and there are planned missions to actually drill in Enceladus and go into the oceans and see if there's microbes. If there are, that would be extremely strong evidence that there's a second genesis of life in our solar system. If that were the case, there'd be really strong evidence that it was ubiquitous.
Everywhere else, yeah.
Not intelligent life, but life. Now, I have a bet with my friend Richard Dawkins, by the way. Everything, I've ran an institute at my university and ran a lot of meetings on the origins of life, which is one of the reasons why I wanted to write this chapter, so I could update my knowledge of it. And my bet, again, because I'd like to be wrong, is that life discovered the only chemistry that works. People said, well, maybe the amino acids, the 20 or 21 or whatever they're used by life, maybe they're different amino acids in other life forms, maybe different base pairs of DNA, because you could imagine that happening. My bet is that physics and chemistry, that enthalpy, that ultimately there's one route that works, and life discovered it, which means if that's true, then all life forms in situations like ours on planets around stars might have DNA with the same four base pairs, have energy powered by ATP. It might be identical. And so I have a bet with him that anytime we discover new life, it'll be exactly the same. But I'd like to be wrong. Yeah. Anyway, that's a long answer to the
so
question.
much.
Sure.
Lawrence, did you want to touch on Venus clouds?
Yeah,
life?
I'll touch on
Because
Venus clouds.
I think that's very interesting.
It is, and yeah, it is and isn't. One of the last places you'd think to look for life is Venus, because it's hellish. It's going to be like the Earth is going to be like that in 2 billion years, by the way. Just wait. Because of a greenhouse effect, not due to the carbon dioxide we're producing, but eventually the sun will be 15% brighter in 2 billion years, and water will evaporate from the Earth's surface, and water is a really good greenhouse gas, and the surface of the Earth will become like that of Venus is now, maybe 500 or 600 degrees Celsius. So you'd think that that'd be the last place to look, but it turns out that clouds around Venus are very dense, and there's a layer of clouds which has a density of water on Earth, and probably temperatures and pressures that are not too different than Earth-like temperatures and pressures. So people have argued maybe there are life forms in the clouds of Venus. And one group of people claimed to find a chemical compound that they suggested was strongly suggestive of life in the clouds of Venus. They were wrong. Okay? But it is a place that nevertheless now has new interest for some people. And an exciting claim was made, and like most exciting claims, it was wrong. That's the thing I want to remind you of. Most exciting claims you will read about in the newspapers in science are wrong. And the real problem with a lot of the way they're reported is they're reported, but when they're proved to be wrong, you never read the stories afterwards. And that's why a lot of people think science is just so faddish. Because today we think this, tomorrow we think that, and it's because all these wrong things get attention. And they get attention because universities and other places want to get money, and so they have press offices that give press releases on these great discoveries. And science journalism has largely ended because newspapers don't have money to generally have science reporters. And so most of them just take the press release and publish the press release. And then that's news. But when a dog doesn't bite a man, it's not news. And so you don't read about it later on when it's wrong. And I think that's a real problem, but that's just the way it is. Anyway, I get to pontificate about so many irrelevant things. Okay, yes.
Hey, Lawrence, how you doing?
Nice to see you.
And
your little one here, nice to see him.
You touched on this, the previous question, but I still kind of trying to visualize the correct way to think about the universe, because, we're used to seeing things with bounds, we can see the edges of them. And when you talk about the universe, there may be nothing on the other side of it. It's a hard concept, right? Because nothing is empty space.
It's a hard concept, yeah.
So, yeah, I know, and it's an empty space, but that's something, isn't it?
Well, as I'm saying, it doesn't have to be any space at all. But, I mean, it's hard to think. In a closed, look, the difference between an open, closed, and flat universe, these are three-dimensional things, they're not two-dimensional. So, and we can't picture them because we live in this, in this world where there are three spatial dimensions, and a flat universe is just the universe that we all think we live in, where, we all feel we live in, where the X, Y, and Z, now that I live in Canada, the X, Y, and Z axes are always pointing in the same direction.
Right.
Curved universes are ones in which the X, Y, and Z axes here are pointing in this direction, but somewhere else are pointing in that direction. It turns out to be three different types of geometry. And flat is exactly what I told you. And closed is closed, but it's not closed like a two-dimensional sphere, it's like a three-dimensional sphere. In a closed universe, you look out far enough in that direction, and you see the back of your head. Okay, if you look far enough in that direction, the back of your head. An open universe is hard to picture. The two-dimensional analogy is often called a saddle. It's infinite in spatial extent. A closed universe is finite in spatial extent. A flat universe is generally infinite in spatial extent. It goes on forever, unless you have something called topology. So in a closed universe, it's just, there isn't any, when you think of the surface of the Earth, you think there must be an inside and outside, because the Earth has an inside and outside. But once again, it could be that the surface of the Earth is all there is. And then if you draw dots on the surface of the Earth and it expands, those dots all go farther apart from each other, and none get closer. But there is no outside and inside. If you go far enough, you don't fall off the edge. You come back to where you began. Right. And my bet by the way, if you want me to bet.
I love the
making
bets.
bets about things that we'll never discover in my lifetime, so I can be, I often say don't make predictions about anything that's less than 2 trillion years in the future. For 2 reasons. It's simpler to make such predictions, and 2, you won't know if I'm wrong. But my bet is that our universe is closed on ultra large scales that we can't measure, and maybe never will be able to measure.
Is it expanding too? Is that the correct way of thinking? Because you hear about expanding universe. Is it actually expanding then, or?
Oh, it is expanding. Yeah, it's expanding, but it's closed. It's just like a balloon getting bigger and bigger and bigger. All the dots are getting further and further apart on the surface of the balloon. Right. And I think the most likely possibility is that our universe is a closed universe, but on scales that, because inflation, if you blow up a balloon very large, if you live in Kansas, the Earth is flat. Okay? It looks flat because it's very big. And inflation blew up our universe to be so big that one of the predictions, it's not always a prediction, but one of the kind of generic predictions of inflation is that the universe is flat. And we've discovered that within the accuracy that we can measure it, the universe is flat. Space is flat. We've measured it to 1% accuracy. Space is flat. But that 1% lives, but I'm saying it's not flat, not at 1%, but some 100th decimal place. It's not, but we have measured it. And that was the reason we, by the way, first proposed what's now called dark energy, because the theories told us the universe is flat, even though the observers hadn't yet discovered that. And there just wasn't enough matter to make it flat. And the only thing was to add energy to something else. Because the geometry of the universe is determined by the energy within it. That's the content of general relativity. The energy and mass and energy of space determines the geometry of space, which then determines the motion of the matter within space. And it's that nonlinear relationship that makes general relativity so complicated compared to Newton. So we needed something else to make the universe flat. But now the observers have measured that on all observable scales, the universe is indeed flat. One of the other arguments that suggest to us that inflation is likely.
Okay, thanks.
Okay, thanks.
Thank you. Go ahead.
Hey there. Thank you so much, first of all, for coming out here to Vancouver. You're fantastic to listen to, so I'm very happy to be here.
Oh, thank you. I
Nice to
appreciate
see
that.
you.
Thank you. It's a pleasure.
So I have 2 separate questions, but I'll go on one, and if there's time, then I'll go for another. One that I'm wondering about is in the direction of gravity, because we don't know quite what gravity is. We know it works. We can figure out the equations for it, but we don't know what it is. Do you believe that at any point in time we will understand what it is, to the point where we can actually work with it and be able to leave space easily rather than need to use rockets and things like that? Do you think that's a possibility?
The first answer for that question is you can guess what my answer is going to be, but my answer is I don't know.
I don't want that though.
I don't know. But let me say but there's part of your question which is actually misplaced, because we do know how to work with gravity. There's this illusion. We got a great theory. It's called general relativity. And part of the fault is the string theorists, who are fault for a lot of things, in my opinion. But one is calling this theory, string theory of everything. It's really a theory of almost nothing. It's a vitally important theory to understand the beginning of the universe and what happens in the center of black holes. But we don't need it for anything else. For everything we can see, general relativity works unbelievably well. So we have a wonderful theory of gravity. It's only those 2 little places we don't understand. Now, they're important from a philosophical perspective, the beginning of the universe we'd like to understand. So we do have a workable theory of gravity. Do I think we'll ever have a theory of quantum gravity? I don't know. I suspect it's not around the corner. I'm skeptical that string theory is, at least, we don't even know what the theory is right now, but it's well motivated. Let me point that out. It's very well motivated. But I'm skeptical because of the requirements in general for a large number of extra dimensions. So I'm skeptical of everything. So I don't know. It's a hard question. But it's the only way we'll ultimately be able to answer the first question that Travis asked. It's the only way we'll unambiguously be able to say what happened at the beginning of time. I can argue what's likely and what's plausible, and I've done that in several books. But I can't argue with the kind of authority that I could if we had a theory of quantum gravity. People work hard, and one thing I will say is there's no evidence that we won't. People say, well, maybe the universe is so complicated that our human intellects will not be able to comprehend it. And that's potentially true. But I see no evidence of that, of some fundamental barrier. Every time there's a barrier, we eventually get around it. And that's why I think it's worth continuing to ask the questions. So maybe someday there will be.
Yeah, and this brings up a tough question. And I know Eric Weinstein and some other people have brought this up, saying that string theory has just been a big waste of time, and all these people.
Well, they don't understand what string theory is.
Right.
I don't think it's a big waste of time at all. It's well motivated, and good people have thought about things a lot, and it's produced a lot of interesting mathematics, but it's also produced useful tools that have been used elsewhere in physics. What it hasn't done is what it claimed to do in 1984, which is unambiguously describe a theory for why our universe has to be the way it is. So it's failed in its original promise, and my friend Frank Wilczek always said string theory is promising and promising and promising and promising. but that's okay. So the hype I used to argue against early on. I got called a critic of string theory. I think even like many false things in my Wikipedia page, it says I'm a critic of string theory. but I'm a critic of the hype. But I wrote a whole book about why it was well motivated in a sense. But it hasn't come to fruition that way. But it hasn't been a failed effort. It hasn't been useless. It's smart people working hard often produce useful things. So yeah, I think people who just say, "Oh, it's been a big waste of time," really, it's easy to say that, but I don't think it's true.
Well, especially coming from Eric Weinstein, where his geometric unity idea,
which I do think is a huge waste of time.
Yeah, it hasn't produced a damn thing, and Eric is out there.
Well, the fact that I'd never heard of it until he started to talk about it online and suggest to me,
right.
I'll get angry letters with this. But anyway, suggest to
Let's
me,
not get angry.
Highly unlikely in my list of likely and unlikely. It's highly unlikely. Just like up there with UFOs being aliens, it's highly unlikely.
Yep.
Do you have another quick question and then?
Yeah, I'd love to. Is it okay if I? Go ahead.
I'm fine with it, as long as these people are.
My other question is about our speed in traveling through the universe, because we're going at such a speed around the sun in the first place, and then the sun around our galaxy and so on. And if multiverses do exist, which I do believe also that there's a very, very good chance that they do, we're probably moving at a speed against them as well. So what would happen if we started going at zero? What if we found a way to go against the speed that we're traveling at and we hit zero? What would happen to our relation to time, and what would happen to the universe around us?
There's a lot to unpack there. We're moving at 200 kilometers per second around the galaxy. And our galaxy, relative to a frame, there's no universal rest frame, Einstein showed it. But there's a frame in which you can look at all the galaxies and ask, are you moving with respect to the average position of all the galaxies? And we're apparently moving at a velocity of about 600 kilometers per second relative to that background. You can actually measure it by looking at something called the cosmic microwave background. Are we moving with respect to this frame determined by the largest structures in the universe? So 600 kilometers per second is big, but it's small compared to the speed of light. Okay, first. So we're not moving at relativistic speeds with respect to that. It's fast, but the effects of relativity at that scale are measurable, but not huge. Okay, but you can't say in what sense we're moving with respect to another universe. It's not well defined if we're causally separated in space. Okay, but Galileo told us that it doesn't matter if we're moving, that the laws of physics are the same if you're moving or standing still, as long as you're moving in uniform motion. So most people say we're standing still right now, but I'm telling you we move at 30 kilometers per second. If I'm on an airplane and I juggle, and I like to juggle every now and then and do magic tricks, I brought some. But if there's no turbulence and the windows are closed, you don't know you're moving. Because there's no experiment that you can ever do, and Galileo was the first one to show this, that can tell you that you're moving at a uniform speed or standing still. There's no meaning to those two things. And those two frames are identical. And one person saying they're moving and another person saying they're standing still, it's relatively true, but absolutely neither person can prove that. In fact, that was the basis. Taking Galilean relativity is what Einstein then realized that claim of Galileo, which is true, we can measure it, is actually inconsistent with the laws of electricity and magnetism of Maxwell, which are also true. So these two pillars of modern physics that were true but inconsistent with each other. And it was the genius of Einstein to say I can make them consistent if I make space and time relative. That's what led him to relativity. Not he just said, oh, well, the speed of light should be constant. It was realizing these two pillars of physics were inconsistent with each other, and he realized that it was an assumption that my time is the same as your time, and there was no experiments that proved that. And in fact, if you could say they weren't, then you could make these things consistent. And special relativity is designed to allow us to have Galilean relativity, which is that no experiment can tell you that you're moving with respect to me and that I'm not moving with respect to you. Both claims are true, and neither is absolutely relevant. Okay?
That's
good. Okay. Thank you.
We have time for these two last questions.
Yeah, two last questions. And then
Hi, Lawrence. How are you?
Hi.
Quick question. I wonder if you know something about new science being discovered at CERN in regards to spinning particles that didn't met
I know what you're talking about. Yeah, I know
the 5% certainty.
Yeah, I've done some of the calculations that they're measuring against, actually, so I know a lot about it. But so at CERN, one of the things you're doing at CERN, and also in an accelerator here in North America at the Fermilab, there's a fundamental particles in nature. One is called the muon. It's a heavy cousin of the electron, and because these particles are spinning, they act like they have spin. Electrons have spin, and muons have the same spin. They have angular momentum, and because they have charge, and they're spinning, the laws of electromagnetism say that they should have what's called a magnetic moment. A spinning charged particle has a magnetic moment. Now, these aren't spinning in real space because they're not really like billiard balls, but they quantum mechanically have angular momentum, and they quantum mechanically have magnetic moments. And the quantum theory of electromagnetism, called quantum electrodynamics, allows us to calculate with unprecedented accuracy. It's the best tested theory in nature. It allows us to predict to 10 decimal places what that magnetic moment of the muon should be. And also other things. And by the way, all of that requires there to be virtual particles popping in and out of empty space. We can never see them, but if we don't include their effects, we get the wrong answer. We get the right answer to decimal places, 10 decimal places, only if we include these virtual particles, which is how we know they're there, even though we can never see them directly. But it's a wonderful way to look for new physics, because if there's new physics on very small scales that you haven't included in your calculation, and the 10th decimal place, it'll produce a different magnetic moment of the muon. And what's interesting is that the measurements of the magnetic moment of the muon and the predictions that come from theoretical physics appear to differ at what's called the 2 sigma level. That means it's 95% likely that they don't agree. Okay? But that's not good enough in particle physics. 95% it happens all the time. Okay? You need to be at the 5 sigma level for us to believe it. That means it's a 1 in a million or billion chance they run. The problem is the theoretical calculation is difficult. Not because the physics of electrons or muons and light isn't understood. When you do the quantum mechanical calculation, there are lots of virtual particles, and some of them are quarks. And it's hard to do the calculation when you have quarks involved, because that's a theory called the strong interaction. And so what people did is say we can't do that part of the calculation, but we can measure the interactions of quarks at other machines, and we can plug in those measurements into the intermediate part of the calculation and get a prediction. When you do that, you get a result that's 2 sigma off, and that's what all the newspapers are talking about. At the same time, however, there's another way to do this calculation, which is numerically. We can't do the strong interaction calculations analytically, but we can get big computers to do those calculations. And those big computers have just come up with the results. And when they do it, they get a result that agrees with the data. We don't know yet which is the right thing. It's tantalizing. And the reason to look at these ultra-precise experiments is because in the 10th or 11th decimal place, it's big. One way is to build a new accelerator that's 10 or $100 billion, okay? Another way is to do a precise experiment and look in the 10th or 11th decimal place to look for new physics. And it'd be a great way to find it. And I've always been interested. That's one of the reasons why I did calculations years ago on a theory called supersymmetry, which would produce new changes in the magnetic moment of the universe. So they're really important experiments, but right now it's indecisive. My bet is, because usually the astounding things are wrong, and since I've been a physicist, almost all the astounding things are wrong, is that unfortunately the new way of doing the calculation, which agrees with the data, is probably right. I'd love that not to be the case, but unfortunately, it'll require new experiments or better computers, and maybe quantum computers can do the calculation better. And so we'll wait and see. Or we'll have new accelerators, and that may happen. Yeah. Again, unlikely.
Thank you.
Before we get to the next question, was there someone in the back that wanted to ask a question? All right, let's move this microphone up.
Okay.
We're looking forward to your question.
It's still, I thought we were going to have an intermission, so we can go on. It's only 8:30. We can go on a little long. I mean, you may have to pee, but I don't really care. Yes? Someone in the back? And then we'll do the question. Was there someone in the back? Okay.
Yes.
Thank you very much. So, what I want to ask was, like, for example, scientific community hits a dead end on some concepts. Let's say nowadays we call dark matter dark energy, or there's a concept of what happens at t=0 and so on. And so what do they do after they hit the dead end? Like, what keeps them going?
Well, that's a really good question. What keeps scientists going is that they actually do believe. They believe that what they're doing is maybe right. You have to work for 10 or 20 years if you're an experimentalist or a theorist. You have to suspect that you're on the right track. When you find out it's a dead end, you do something else. That's what's wonderful about science. The most beautiful, elegant idea in the world, when you find out it disagrees with experiment, gets thrown out like yesterday's newspaper. Elegance doesn't matter, beauty doesn't matter, no matter what some people say. It just, you change your mind. That's the lesson that this book is about, and that we should teach people, is that's the difference between science and dogma. With dogma, when the evidence goes against your dogma, it doesn't matter. The dogma must be true. Damn the evidence. In science, we're willing to change our minds. And I've said this before years ago, but I'll say it again, that what I hope for every student at a university is that at some point in their education, some idea that is so central to their existence that it defines them turns out to be wrong. Because that's the liberation that education and science provides. And only then can you realize that are you willing to open your mind up to the idea that you might be wrong. And so it's a liberating thing. And as a scientist, I've been wrong so many times that it's liberating. It's hard to do at the beginning, but it's an incredibly liberating thing. So if it's a dead end, the best thing to find out is that it will be a dead end. What's unfortunate right now is that we haven't been able to, we don't know. I'm willing to bet that dark matter does exist in a new type of elementary particle. I think the evidence is, my own opinion is that that's highly likely. And I've proposed experiments to look for it 40 years ago, and then I thought they'd be done in 5 years, but those experimentalists, it's hard, and so they take time, and that's why I like being a theorist. But I think that's likely, but it could be that we don't, at the level the best level we can do, and in the next generation of experiments will be that we don't find evidence for particle dark matter of the type we thought, and then we'll just have to say that that's wrong, and we'll go in another direction. But that's fine. That's what science is all about, at the edge of knowledge. Okay?
Right,
it's a good question.
Thank you.
Thank you.
Thank you. It's a good question. Okay.
Go ahead.
I guess we're having more than, yeah?
So speaking of dead ends, I'm a postdoc at the University of Victoria. And the question is actually related to dogma. So given that university departments are kind of bleeding with ideology and identity politics, do you have any advice for early career researchers who are looking to get into the academy, but also keep their job?
You're in, it's, my first advice is the same advice I give to all young people, which is don't let the bastards get you down. I mean, literally, just keep plugging away. The likelihood is not great of getting a job necessarily, but you're doing it because you enjoy it. You're not doing it to please someone else. You're doing it because you enjoy it. And the skills you're getting will be ultimately useful no matter what you do. But, this is gonna, well, I said this in public, I guess, in writing, so I guess I'll say it in public instead. It's very difficult to get a job right now if you're a white male. It is, it's just the way it is. But that doesn't mean it's impossible. And so really, you just have to continue to ask yourself, why am I doing what I'm doing? Am I enjoying it? Am I getting some personal benefit out of it? And realize that the path that you may ultimately take may not be the path you expected to take. But it may be a better path. I mean, I know some very, 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 very ultra-rich failed physicists who, the guy named Nathan Myhrvold, who used to work with Stephen Hawking, he wasn't good enough, but he then went to Microsoft and became a billionaire. Sergey and what's it, the two of them, if one founded Google, they're not computer scientists now, but they own computer scientists. But I really do think that you just have to try and remember often in your career why you're doing what you're doing. It's discouraging, but it's not impossible. And keep plugging away. Just keep plugging away for the sake of plugging away, and you never know what's going to happen. I mean, it's what governs my life right now. I've had a lot of discouragements, and just keep plugging away, because why not? And a friend of mine who's had a lot of other discouragements, and I've done a podcast with, Woody Allen, has said, and it means a lot, just keep working, because it provides a distraction from the fact that the universe itself is meaningless. Okay?
Awesome. Thank you.
Thank you. Okay, good. Thanks. Anyway, good luck to you. Really good luck. Best of luck to you. Mm-hmm.
Go ahead.
Thank you for crossing the Great White North, and I thought that you should have some rewards for that.
Thank you.
And I was listening the other day, you were talking to Kurt Jaimungal.
Yeah.
I don't know when you recorded it, but I only listened to it a couple days ago.
Yeah, it was recorded recently in the last month or two.
Yeah, and it was very interesting, but I'm not sure what part of it was that triggered me to think about dark matter, continue on the theme of dark matter. But there was an opportunity in the YouTube to put in a query. I'm sure you haven't had a chance to look at it. My query was, is it possible to take a bit of dark matter and contain it in some kind of container? And then I realized that I can go down to the local liquor store and buy some dark matter.
There you go, okay.
And so I thought you should have a little reward and have some dark matter.
Oh, can I?
So there you go.
Well, there we go. You can look at that. Wow, this is great. This is absolutely great. I won't get a Nobel Prize for this, but this is good. Thank you very much. Yeah, no, I'll answer the YouTube question. The dark matter is dark because it doesn't interact with electromagnetism. It really should be called invisible matter rather than dark. But that's what allows things to be held in containers, is electromagnetism. The reason that we exist as material bodies is electromagnetism. It's not gravity, right? Just to give you I've talked about this before, but I would tell my students this, to give you a sense of how utterly irrelevant gravity is, okay? You take the entire mass of the Earth, all of the mass of the Earth to be pulling me down, but the few atoms in this floor are holding me up against all of that Earth. It's just electromagnetism that stops me flowing through. So gravity is just irrelevant compared to electromagnetism. And so if you want to put something in a container, you need a way to, you need to have a force Contains it. And the force of electromagnetism won't work with dark matter. Doesn't mean there isn't some other way to imagine doing it, but any kinds of things, magnetic bottles, all that requires electromagnetism. And so dark matter flows through things, and that's why we can look for it, we think, because if it's elementary particles, it's not just up there. It's in this room going right through your bodies as you nod off right now. And it goes right through the Earth without knowing the Earth was there. And that's why we can build experiments underground, because most of the particles go right through the Earth, but they don't have zero interaction, at least the particles we think about. They just have very weak interactions, and every now and then one of them will collide with an atom. And if we have a big enough detector underground without any radioactivity for long enough, we might witness an event. That's the idea. But containing it is not possible. The best example of a dark matter-like particle is my favorite particle in nature, which you probably know is my favorite particle, the neutrino. And neutrinos from the sun, which are going right through you, about 1,000 billion through every square centimeter of your body, every second of the day, day and night, day from above and at night through the Earth and up through your body. They can travel, on average, through 10,000 light years of lead without a single interaction. And so it's hard to contain neutrinos, too. But that doesn't mean it's impossible for us to detect them. It's the beauty of modern science, is that we can build experiments that are incredibly sensitive to incredibly rare events. And it's so difficult that that's why I'm not an experimentalist, because it's hard, and I admire tremendously. I propose the experiments, and then they have to do them. I was on an experimental collaboration, the large one that I think will be the largest one, but I'm not on it any longer.
All right, last question. Here we go.
Thank you. If you don't remember me, I was the guy who yelled white earlier.
Oh, okay.
Yeah, I actually asked you if you could sign my girlfriend's book, and you said yes. And funny enough, we forgot to bring the book. So if anybody has a book,
the good news
just
is
anything written by.
It's good you asked that question because he can give an answer.
Yes, we do have some books here tonight that I have backstage. We only have 15. Yeah, we'll. But they are available online. Amazon can get it to you in like.
I would like you to sign my
seconds.
online book. I believe that's somehow possible.
Your online book? Yeah, I have signed Kindles on the back, to the front.
I meant through the internet. It's a joke. Yeah, I'm trying to be less serious. Thank you very much. Bam Margera really turned himself around tonight, you guys. And Lawrence, you remind me of an old me. And mathematically,
an old you.
That is a correct joke.
Okay.
But I started writing stuff down once you started talking about a closed universe. And I just wondered what's at the end of that closed universe. And then I started thinking more about some of the stuff that I've read that you said, maybe that we are inside of a black hole. And you said that the cosmic background radiation is what we use as a reference to judge our speed. So could that be even thought of as perhaps the event horizon? We're looking at it from the inside.
It's a good question. The answer is no, but it's a.
But is that true?
The answer is no, because we know what surface that cosmic microwave background comes from. It's not Hawking radiation from the event horizon. We know that. If there were an event horizon in our universe, and if our universe was a large black hole, the temperature of that radiation, so the temperature of the microwave background we can measure, it's about 3 degrees, 2.735 degrees Kelvin. That's 2.735 degrees above absolute zero, the temperature in northern Canada or something. But if there were an event horizon and Hawking radiation, due to the observed universe being a black hole, the temperature of that radiation would be about 10 to the minus 42 degrees Kelvin. So it's orders and orders of magnitude below what the cosmic microwave background radiation is, and we know where that comes from. But we could be living in a black hole, which is a fascinating thing. A closed universe dominated by matter is essentially a black hole. A closed universe dominated by energy is not, because it'll expand forever if it's dominated by the energy of empty space. But it allows me to make a segue about black holes, which may be interesting to others if my answer to your question isn't. Black holes are very exotic, and there's lots of movies about them and all sorts of stuff. But they're exotic, but they're not that exotic, okay? Namely, if you took a small if I took the mass of the sun to make it into a black hole, you'd have to squeeze it to be the size of the metropolitan Vancouver area. Okay? Be very dense. Each teaspoon of material would weigh hundreds and hundreds of billions of tons. Okay? So that's pretty exotic. Okay? But if I took a black hole the mass of our galaxy and squeezed it, if I took all the matter in the galaxy and squeezed it, at what point would it become a black hole? The average density of that material would be the density of water. And if I took the mass of our observable universe and asked what would be the average density of that material if it were actually a black hole, it would be within a factor of 2 of the observed density of the universe. So it's not so bad if you're living inside a black hole, if we live inside one. We're just not in the latter stages of it. So the nature of black holes is very different depending upon the mass of black holes. But they're all equally interesting because ultimately, in their final collapse, they defy the known laws of physics. And in my book, I talk about strange things. Time becomes space, and space becomes time. But anyway, your question, which is a good one, can be answered with a definitive no. The cosmic microwave background is not the Hawking radiation from the event horizon, because we can actually calculate what that would be, and it's 42 orders of magnitude different than what we measure, which is pretty definitive.
So if you think it's so definitive,
well,
like, you believe it is, right?
I don't believe in anything.
Almost.
Yeah, almost. No, not even close.
But let's just think, for example, that we made up all these numbers to make things make sense. We made up dark energy and dark matter just to make our math make sense, right?
Yeah, that's what
so
people
you
think.
can't prove that those exist. So
No, that's
let's
not
just
the way it
ignore all
works.
that. Oh, sorry. Let's ignore all that. And I'm going to ask you a completely different question.
But let me just say, no one invented this stuff because we wanted it to be there. Physicists were dragged
because it's easy.
Physicists were dragged kicking and screaming to the realization that it might be likely. And in fact, the real candidates for dark matter, the only kosher candidates, and I'm happy to use that word today, the only kosher candidates for dark matter are the ones that were predicted from particle physics to exist before it was realized they could be dark matter. And those include the supersymmetric particles of the supersymmetric standard model, particles called axions. All of these were designed to solve problems in particle physics. And it was only after the fact that it was realized that in the early universe, they would naturally be created with an abundance that could be dark matter. So they weren't designed to fill the holes or to mimic or, they weren't done any of the things you say. They were there for a good reason. And then after the fact, we discovered this fact. So often people say these things, but they're wrong, just like you were.
Yeah, no, you totally proved me wrong there. And I've been saying it the other way. Do you think that if we ever met another species, that our numbers would line up?
It's a fascinating question. The answer, of course, is I don't know. But I suspect that, I think any intelligent species, mathematics appears to be the language of the universe. And it would be very hard for me to imagine, but I could be wrong, that any intelligent species would not discover mathematics, because mathematics describes the universe that we live in incredibly accurately. In any advanced civilization, since we can actually measure that the laws of physics are the same throughout the universe, and to high accuracy, let me emphasize that. We can measure that to in some cases, many decimal places of accuracy, that the laws of physics are the same there, here, and there, because we can test it. Then I think any sufficiently intelligent civilization will understand mathematics, and that's why Carl Sagan, when he wrote Contact, it's what will you broadcast if you want to prove you're intelligent? And one of my favorite episodes of Star Trek, the first 10 prime numbers, the first 20 prime numbers, because it indicates you know mathematics and therefore you have intelligence.
Every single one of my alarms is set to a prime number.
Okay, there we go. Thank you very much. And
thank you everyone. Big round of applause for Lawrence Krauss.
Thank you so much. Thank you so much. Thank you.
Now, let's all go hang out in the lobby. We'll be out there in just a minute. I have some books available for sale, and I've heard Lawrence will sign pretty much anything, so
And
get ready for
I
that.
might do some magic tricks out there too, 'cause
And
you know I love magic.
Yeah, and Lawrence brought some magic tricks as well, and he blew my mind earlier. But he gets to hang out with Penn Jillette all the time, so he's got a huge advantage.
Yeah, I know, but Penn didn't teach me these tricks, but he's much better than I am.
All right,
I'm
thank
pretty
you,
damn good,
everyone.
though.
We'll see you in the lobby.
Thanks.
Thank you.